The fastest known pulsar used to be this particular one, PSR for pulsar, its right ascension, which is like longitude, and its declination, which is like latitude, and its period is in milliseconds. Look how accurately it is determined. And some of that 4 at the end is not experimental uncertainty. It's because the pulsar is very gradually increasing its period. And this fast pulsar sounds like this. Sounds like a kitchen blender. It's going at about 700 hertz. And this is getting interesting. Because if a pulsar, they believe, goes much faster than that, it gets some instabilities in its core, and more of this gravitational radiation is emitted, and that loss of energy prevents the star from spinning up faster. So pulsars shouldn't go much faster than that. They've recently found one that's going marginally faster, and you see, because it's more recent observation, we haven't got it to so many decimal places. Though to be honest, there's probably more by now. But it's about 1.4 milliseconds. And of course the hunt is on to find an even faster one, because that will break the theories, and that's really what research is about. The first planets discovered beyond the solar system were planets around a pulsar. And the way it happened was from Doppler shifts. I've already talked about a pulsar orbiting another star. As a pulsar orbits another star, when it's coming towards you, the pulses pile up on each other, period seems shorter. When it's moving away from you, period seems longer. And radio astronomers routinely do that for pulsar orbits. But if you have a planet orbiting a pulsar, some visual aids, pulsar, planet. As the planet goes round, it tugs the pulsar just a little bit. And even if you can't see the planet, the radio astronomers through the Doppler shift can see the tugging of the pulsar and measure it. And by doing that over a fair number of years, they've been able to work out that this particular pulsar, and it's one of few, has 3 planets plus a little asteroid type thing as well going around it. Also, from studying Doppler shifts on orbits, the roundest known thing in the universe is the orbit of a pulsar around its companion star. The orbit is circular to within 5 microns, and the orbit's 567,000 kilometers. So that's an eccentricity of about 10 to the minus 7. And finally, if something falls onto the surface of a neutron star, it hits the deck traveling at 60% of the speed of light. So strong is the acceleration due to gravity. I don't know about you, but I find these things a little bit hard to believe in. They are incredible. But unfortunately, they're real. And everything I've told you is, to the best of our understanding, true. So, thank you for your interest.
We don't have very much time for questions, but I will take 3. So, anyway.
So how do we know anything about a neutron star below the shell?
Right. We don't know a lot. Most of what I've been talking about is modeling, theoretical predictions. But there are instances where a pulsar rapidly changes its spin, which I won't go into, but there are instances. And after that rapid change of spin, it recovers exponentially back to its original spin. And that exponential recovery is due to all the superfluid inside. You know the way of telling the difference between a raw egg and a hard-boiled egg without opening it? You spin them up, and then you dab your finger on it to break it, stop it. The solid one, hard-boiled one, stays stopped. But when you lift your finger off the raw one, it starts spinning again, because you've only stopped the shell, not the yolk, which is still spinning, and gradually it recouples and starts again. So the recovery of a pulsar after one of these hiccups is a bit like the way a raw egg continues to spin, even when you stop breaking it. That's so far really the only firm evidence there is. But it fits.
Yeah, thank you.
Anyone? Do we have any more questions?
I've heard there's been models, hypothetical models for stars even denser, like quark stars, Grion stars.
Yeah.
Is there anything experimental on that, or is it still hypothetical?
There's theoretical work being done on quark stars, because if they find something spinning much faster than that kitchen blender one that I played you, it has to be a quark star. Quark stars can spin faster, and I think it can be more massive but more compact. May not have got those quite right order, but they can certainly spin faster. So there are people doing theoretical work on what a quark star would look like and how fast it could spin. But as yet, we have no experimental evidence for it. But there's always the future.
Thanks. All right, one last question, guys.
I'm around till Sunday evening if you have other questions.
Okay, fantastic. Oh, one more. All right, perfect.
Quick question. When you were mentioning the iron polymers, you said that you need massive pressures in order to create them. Do we have those kind of pressures on Earth? Have we ever seen iron polymers on Earth?
No, I don't know that we have ever seen iron polymers. We can certainly see in strong magnetic fields that atoms that were spherical become cylindrical. So that's established. And Larmor has done some work on how the orbitals would be and that kind of thing. He probably didn't envisage this kind of magnetic field, to be fair.
Thank you.
All right, well, thank you again, Professor Bob.
Thank you.